Our next speaker will be Babak Enayati from National Grid. Babak received his PhD in electrical engineering from Clarkson University, Potsdam, New York in 2009. He joined National Grid USA in 2010 and is currently the manager of the technology deployment team, which is responsible for development and implementation of the transmission network modernization strategy. Babak is a senior member of IEEE and currently serves as the IEEE Power and Energy Society Governing Board member at large. Babak is also the vice chair of the IEEE Standards Coordinating Committee 21 and the IEEE Standard 1547, a standard he's very passionate about and he's going to cover in his presentation today. It has to do with the standard for interconnecting distributed energy resources with electric power systems. Babak is registered as a professional engineer in the state of Massachusetts. Please join me in giving a warm virtual welcome to Babak Enayati. We are now going to assign presenter rights to Babak.
Excellent. Thank you, Wayne. Can you hear me well?
Yes, loud and clear. Loud and clear. Thank you. And we see you as well, so this is great virtually. And by the way, Babak, welcome back again. You spoke last year at the Distribution Automation Workshop in Houston, and it was a resounding success. And one of the big feedback items we heard directly from the utility and customer attendees that were there is they wanted to hear even more about Standard 1547 and how power quality plays into that. So very much looking forward to having you back again. So thank you.
Absolutely. Thanks for inviting me, and I wish we had this in person, but glad to be here and look forward to attending next year's workshop as well. So by the way, one comment on this picture, the yellow tie that you see I'm wearing in this picture was actually a gift from Dr. Amin. So Masood Amin gave this to me. So I'm not sure if he's on, but I invited him to a session in Massachusetts to give us a talk, and I told him, hey, I like your tie, and he gave it to me. So anyway.
It was my pleasure, honor for me, sir. Thank you for wearing it. You look dapper, much better than I did. Thank you.
Thank you, Masood. Thank you. Okay, so the next 20 minutes or so, I'll brief you on some of the highlights of the IEEE 1547 and the work that we did at National Grid in terms of impact of distributed energy resources on the electric power system, power quality, and I'll be happy to take some questions in the end. So all right, so then agenda for our presentation. First, I'll start off with some power quality sections in the IEEE 1547. This, if you're not familiar with the standard, this is a standard that is widely used in the world, which basically applies to distributed energy resources interconnection, or I should say integration, to the electric power system on the distribution side. And so I'll highlight some of the recent power quality changes. The standard went through a major revision. It was published, the newer version was published in 2018. I believe it was like April, so a lot of new requirements on many like smart DER functionalities, but today's focus will be on the power quality. And also in the end, I'll share some of the National Grid's experience with smart inverters. There are some challenges in terms of implementation of some of the smart functions, and we'll review those challenges as well, and some of the potential solutions that can be made. So starting with flicker, in terms of the IEEE 1547 standard, the 2003 version of the standard said flicker, the DER shall not cause any objectionable flicker to the DER, to the loads on the same circuit, the distribution circuit. And this newer version, we basically define what that objectionable flicker means. Okay, so so those who are familiar with flicker work, we have two indices: short-term, long-term indices, and this table basically defines those the emission level for both long-term and short-term. Both long-term and short-term indices are defined in the standard, but our base for these discussions and requirements were IEEE 1453 guide and IEC 61000-3-7 standards. I'm not going to go through the details, but the point is the table addresses or specifies the limits in terms of flicker on the DER facility. Next topic is on harmonics. So many utilities are concerned as we add more and more of distributed energy resources on the distribution system. Even though each DER is within the acceptable limit in terms of harmonic distortion, are there any concerns in terms of total harmonic distortions on the circuit? So that's just an open question. But what we did in this 1547 section, we specified the harmonic limits for each DER facility. Okay, so it can be one DER or multiple, but so the two tables here you see, table 26 and 27, specify the maximum odd and even harmonics for each DER. Okay, and the 2003 version of the standard did not have the even harmonic table, but as we were seeing higher and higher magnitude or number of power electronic devices connected to the grid, plus nonlinear loads, it's anticipated that we will have some even harmonics on the system. So we define the limit for those harmonic levels as well. I don't have another slide on this, but just to let you know, interharmonics are also addressed in 1547. So say third harmonic, fourth harmonic, but how about interharmonics, the frequency spectrum between those two integer numbers, right? So that's also, the limit is also defined in the standard. The other change that was made to the standard, to the previous one, is the term TRD, total rated distortion. It used to be THD, total harmonic distortion. We changed that to TRD. TRD is basically THD at rated current. Okay, so UL 1741 is going to connect the inverter to a rated load, and inverter is generating rated current. They will measure THD and they call it TRD because it's measured at the rated current. That's pretty much it. Moving on to next slide. So the next couple of slides, I'm going to quickly cover the concept of system grounding. But before we get there, and the reason that we talk about system grounding is we want to see the impact on system overvoltages. Okay, but before we talk about voltage issues, let me introduce two concepts here, or two terminologies, because we're going to use both in the next couple of slides. The first concept is called, or first terminology is called transient overvoltage. So transient overvoltage is basically the instantaneous, maximum instantaneous voltage at the first overshoot when the voltage changes. Okay, so your voltage will never go from one point or magnitude to another without any oscillations. Depending on how stiff your system is, there will be some oscillations. But the first point here, the maximum instantaneous voltage, the first overshoot is called transient overvoltage. Temporary overvoltage is the RMS of the voltage once it's settled at the new magnitude. Okay, so temporary overvoltage is RMS. Transient overvoltage is instantaneous. So with that in mind, so let's see what the standard says about overvoltage challenges caused by DER. typically, well, most of the distribution systems in the world, I should say, not just US, are designed to be effectively grounded. What does that mean? If you have a line of ground fault in an effectively grounded circuit, the voltage in the unfaulted phases will not exceed 138% over voltage. Okay, so as we add more and more distributed energy resources, if they do not provide that ground source to the load, and you have a line of ground fault in the system, and the first upstream recloser opens on the distribution circuit, now you lose the ground source from the substation. Now all the DERs connected to that island, if they don't provide the ground source, but they're capable of pushing the voltage up on the unfaulted phases, you can end up having really large over voltages on the unfaulted phases for a line of ground fault. Okay, so the standard is limiting that by saying the DER shall not cause the fundamental frequency line of ground voltage on any portion of the area electric power system that is designed to be effectively grounded according to the IEEE C62.92.1 standard to exceed 138% of its pre-fault condition. Okay, so that's actually a definition of an effectively grounded system. And the standard says, so as you add more and more DER, that requirement, 138% over voltage, cannot be violated even after DER connection to the grid. The other requirement in terms of voltage is called transient over voltage. So the limitation on the cumulative instantaneous over voltage. So I'm going to actually move to the next slide. I can explain this better here. One of the challenges that we're starting to see in the industry in terms of voltage issues is not only steady state over voltage, but more also transient over voltage as well. Okay, because the penetration of DER is growing, and it's time to pay attention to even sub-cycle over voltages. And so what we did, this is all new, it did not exist in the old standard. What we did, we looked at, so what's out there in terms of available documents that we can use to specify the even sub-cycle requirements for over voltage. So we looked at the ITIC curve or ITIC curve, SABIMA, also known as SABIMA curve. We looked at Hawaii interconnection guideline. They have transient over voltage requirements, and then we compared those with typical surge arresters damage curve. Okay, so, and we came up with this figure or the curve that you see on the left side. There is an acceptable region, so as long as the voltage for the period of time, the cumulative period of time, it stays within that acceptable region, then typical distribution system surge arresters should be fine and not get damaged. On the right side, there's an example of how you calculate the cumulative duration. So look at this red curve. Well, hopefully this won't be your system voltage. We're kind of exaggerating this for demonstration purposes. But assuming that the red is your system voltage, you see that it's exceeding the blue dotted lines 3 times, X, Y, and Z, right? So within 1 minute time window, you're going to calculate how many times the red crosses blue, and then you add all of those times. That becomes the cumulative duration on figure 13. Okay, so you put that number there and see if the blue line is within acceptable region or unacceptable region. So that's basically what the standard specifies. In terms of solutions, some of the potential solutions that should be considered or can be considered for some of the issues that I just mentioned. If you're having steady state voltage fluctuation, okay, so cloud transients on your solar facilities causing voltage fluctuation, what is a solution? A potential solution can be actually DER, regulating system voltage. So there are 4 different modes of voltage regulation with reactive power and 1 mode with active power specified in the standard. The reactive power modes are constant power factor, volt-var, watt-var, constant reactive power. And another mode is called volt-watt, which is basically regulating system voltage by adjusting the output active power. Anyway, so those can be considered as solutions for steady-state voltage fluctuations. In terms of harmonics, it's just in case you see the harmonic levels are increasing. Filtering, of course, is the obvious solution, and also in terms of groundings, system grounding. If you see that DER is not providing ground source and is capable of increasing the voltage on the unfaulted phases to a level that is very dangerous to your lateral, to the loads, single phase loads under laterals and the unfaulted phases, adding ground sources can be considered as a potential solution, like grounding transformers. So that's it on the standard side. I'm going to move up to National Grid's experience with smart inverters. We have National Grid was allowed to own and operate solar generation and battery storage for R&D reason. You typically don't own generation, but this was an exception awarded to us by DPU, Mass DPU, so that we can do more R&D work on smart inverters. Okay, so you see all the cost information here. I'm not going to go through that later. I'm not going to go through that now. You can take a look at it later. But let's focus on the technical aspect. These solar facilities, and again, including some of those facilities have battery storage as well. The control schematic or the way we control these facilities is shown here in this slide. So an operator, for now, none of these control schemes are connected to our GMS system. So everything is isolated. Now we're still at the testing phase. So I can actually log in to this Trimark control platform from my computer through home Wi-Fi and make a setting change to the solar inverters here, right? Say like, hey, I want to change the power factor from a unity to 0.95, and send a command signal, and that gets implemented within 2 seconds. So we can remotely control these inverters and the settings. The point I'm trying to make there is basically why a communication is important. We're going to get to the power quality aspect, and you'll see how how we can connect the dots. But on this slide, here's an example of a secondary of an interconnection transformer. The orange or red, I think it's orange, is voltage, and that secondary side with volt-var function being off. So it's a cloudy day, voltage fluctuation is seen here, is going crazy, but we turn on volt-var, you see the voltage is improved. When I say improved, meaning the voltage fluctuation is improved, so therefore the system power quality is improved as well. And so what I'm going to do in the next, I think, 3 slides is one of the biggest questions we have on the utility side is are volt-var settings or power factor settings or reactive power settings all impacting the system power quality? Are these like just one setting that applies for the entire circuit or entire area? The answer is no. each power factor setting is location specific. Each volt var setting is location specific. Okay, so you can't have this one power factor working for all cases, your DERs in your system. So in the next couple of slides, I'm going to actually show you the equations that we came up with. We won't spend too much time on proving those equations, but more like presenting how you can set the power factor of your smart inverters or volt-var functions of the smart inverters, because those are directly impacting the system power quality. So starting with power factor setting, what you need to do first is put a fault on your ASPA model, any other software you're using. Put a fault on the high side of a connection transformer and look at the equivalent Thevenin impedance and also R and X values at that location. So equivalent Thevenin R and X. Okay, and so that's it. What you need to do then is to add the impact of the interconnection transformer to your equations as well. So your X over R ratio, the adjusted, we're going to use this equation to consider the impact of the interconnection transformer impedance on your RNX, calculated RNX on the primary of the interconnection transformer. So once you have the adjusted X over R calculated, then the power factor of your DER facility can be calculated using this equation. Okay, so let's spend a couple of minutes here to I understand. So what are the variables in this equation? X and R, right? Both adjusted and the the primary side of the connection transformer. So what does that mean? If I have a DER facility closer to the substation, of course X and R are going to be different than the ones at the end of the circuit. So power factor, the calculated power factor, is going to be totally different between DERs closer to the substation and those that are connected to the end of the circuit. Okay. So that's the requirement or the way of setting the power factor. I have one more requirement or way of setting the volt-var curve, and then we should be good to go. The text you can read later. The message here is basically we have areas that the voltage exceeds 1.02. The 1.02 was a default for for national grids acceptable over voltage. Okay, so it may be different for yours, but we picked 1.02 as the reference point in terms of voltage regulation. Areas that the voltage exceeds 1.02, you consider that as region A. Region A means like these DERs are actually very close to the substation. Okay, as you go along the feeder, for the distance increases from the substation, we're going to have voltage drop. Okay, so for region B, you may have you will have a different volt-var curve compared to region A. Okay, the reason for that is region A requires less reactive power for voltage regulation. The voltage is already high in terms of voltage injection. Okay, so pick a point here under voltage, like say 0.96. You see that the blue curve requires less reactive power than the red one. Okay, so the red has a higher slope for region B. So what am I saying here is basically as the volt-var setting to respond to your power quality issues is location specific. And you can use this equation. This is more like, I kind of explain where this is coming from, but in order to properly set the volt-var curve, you can refer to this equation as well. We had 18 sites at National Grid with smart inverters, and each site had its own power factor and its own volt-var curve. We did not find any volt-var curve that was like 100% match, and for the reason that I just explained, right? And that reason was what? The distance, the location, and X over R ratios. So those vary, and as those ratios vary, then you're going to have totally different settings for your volt-var curve. So where am I going with this? As you add more and more distributed energy resources to the grid, things change. Things change in terms of the impact on the existing volt-var curves. So the slope of curve is going to change as you add more DER to the grid with reactive power capability. Now, there is no guarantee that all these DERs are going to be on all the time. Okay, so one can be off tomorrow for maintenance reason, so no manpower can actually manually go to the facility and keep changing volt-var curves every day. So that's why we need systems like AGMS or DERMS to remotely monitor the status of each large-scale DER and adjust the volt-var curve based on the available reactive power resources in the system. Otherwise, just one voltage setting, volt-var setting, and power factor setting is going to be extremely challenging in terms of impact on the grid. And that's it for me. So I'll be happy to take a few questions.
Babak, thank you very much for that great presentation again, and the update on DERs and having a major impact on the grid for sure. And I think we're just probably going to see more and more of these come on the system as we move more toward alternative energy and the changes that are happening in the future of the grid for sure. So I'll again pass the mic over to Eugenio to see what questions there are from the audience. Eugenio.
Thank you, Wayne, and thank you, Babak, for the presentation. There is a question coming in and referring to slide 77 that you presented. Which mode is recommended for participating in voltage regulation? Is volt-var a better option?
Okay, that's a good question. So volt-var has its own advantages, and that is when the voltage is good, an acceptable range, there's no need to inject or absorb reactive power. That's unlike power factor, constant power factor, or constant reactive power mode. So in terms of system performance, yes, I should say volt-var provides benefits that will be seen by the system operators, but it's a little bit more complicated when it comes to implementing it compared to, say, fixed power factor or fixed reactive power mode. Complicated in the sense that volt-var functions need to be coordinated amongst DERs, and that requires some sort of communication system in place.
Thank you, Babak. One more question. We have time for one more. So we see the National Grid solar site you showed us, and as the IEEE 1547 standard evolves and add new requirements, are you having to change equipment, like for example the inverters?
No, we're not changing the equipment. The new 1547 has many smart functions required for DER. National Grid has been testing these functions in the field to make sure that we're comfortable with those functions before we allow our customers to actually utilize these functions. So that's the purpose of these solar facilities that we own. We've been implementing, say, like voltage regulation, frequency regulation, and so on. But we're not going to replace the existing. We're not going to go back and retrofit the existing DER. It's more like future customers, when they inverters that are compliant with the new 1547 are available. We want to make sure that from a system operations and planning perspective, we're ready to accept or not accept, to study those applications.
Okay, thank you, Babak. And Wayne, back to you.